All right, let's go ahead and get started here. I want to remind you that you have a quiz on Canvas. It is due tomorrow evening at midnight, and it will close then. So if you haven't finished it by then it will just close on you, and whatever you've done, it will submit that. So make sure you plan time for that. And the quiz code is up there. And for those of you who can't see that board, it's right here. Q611222. I have put together a homework assignment that goes over some of the kinds of problems that we're going to be working on in class today. I didn't want to make it due at the same time as the quiz, so it's due on Sunday, but remember that you have a test on Monday, so I wouldn't wait until the last minute to do that homework assignment. It is going to help you prepare for the test, but if you're struggling with that homework assignment on Sunday night, you don't have the opportunity to ask questions and get help on it, so I would start working on it sooner than that. And then you have a vocabulary assignment for chapter 14 that is due on Sunday night. I would make sure that in that vocabulary assignment, any vocabulary that is from the first couple of sections of chapter 14, and I'll let you know more details on what I mean by first couple on Friday, make sure that you know those and have prepared for those to appear on the exam. Any questions? Okay, I had a question about the final exam in the earlier class, so I'm just going to kind of repeat what I ended up telling them. Your final exam has two parts. 1 hour will be an exam of my writing that will be comprehensive, but focused mostly on the acid-base stuff, since that we won't have covered on the previous exams. And then the second half will be the ACS cumulative exam for the year. So a couple of things to keep in mind. This is a normed test, which means what they try to do is make the average 50%. So we think of average as being like a C or a B, C, but 50% is not a C or a B, C normally. So if you had 50%, that would actually be just fine. In reality, we're not going to cover all of the material on there. So even less than 50% is actually what our average is. So out of 50 questions, our average tends to be 20, 21 right out of that. Okay, so it's challenging. That's not to say don't prepare for it. You do want to go and look over your material. The most important things to remember from the fall are going to be stoichiometry, which we talk about on again, off again here, but especially in converting grams to moles and using moles for things. So we use moles to find molarity of solutions and concentrations and things like that. And you probably want to look at the gas laws. There's a pretty big section on kinetics because there's lots of different questions we can ask about kinetics, but on the test, it's called dynamics. So don't let that word throw you. Dynamics just means kinetics. Okay, final exam for this class is Monday, I think the 2nd of May at 9 a.m. So even though this class meets at 10 a.m., the exam is at 9 a.m. Okay, and I know we went through this last fall, but it can be really easy to kind of get in your mind, class starts at 10 a.m., but the final starts at 9. So make sure you are here at 9 a.m. If you have several finals on Monday, and you would like to take it earlier, I have a couple of seats available in my 9 a.m. class. Their exam is on Friday at 9 a.m. So I need you to let me know ahead of time so I know how many tests to make. And it does depend on there being seats available. So if everybody wanted to take it on the Friday before, I just wouldn't have enough seats for you guys to be able to do that. So if you think that you would like to get the exam done early, let me know sooner rather than later. First come, first serve. All right, any other questions? Yeah.
For the ACS section, do we get a grade that affects our history grade?
Yes, but what I will do is weight it more towards my final. So the question was, does the ACS portion affect your grade? So keep in mind that the final exam is, I think, something like 10% of your overall grade. So it's a pretty small chunk of your overall grade to begin with. And probably what I will do is my portion will be like 75% and the ACS will be like 25%. So it'll just be a very small portion. I will not let the ACS portion of the exam make somebody who is an A student become a C student or anything like that. So if you're worried about something like that happening, no. Your final exam could possibly make your grade go up or down by half a letter grade, but it shouldn't change it by more. Okay. All right. So let's get started. I'm going to go through several problems that are equilibrium problems, many of which will use the ICE tables that we were talking about on Monday. And then I'm going to save the last few minutes to talk a little bit about the Le Chatelier principle. You've looked at that in lab. We've talked about it a couple of times in class. I want to kind of get all of those ideas together and we'll talk about that. All right, so I find people like to know what it is they're going to be asked to do. So this is the kinds of things I might ask you to do on your quiz and on your exam. This should pretty much reflect what you see in the objectives or the goals for chapter 13 on Canvas. But you should be able to write the expression, which means write with the chemical formulas what K or Q are. You should be able to calculate K or Q by plugging in their values. You should be able to determine the direction of the reaction from the concentrations. That was what we wrapped up with in the packet on Monday. And I will collect that packet on Friday so you can use it to look at during your quiz. And then determining equilibrium concentrations from the initial concentration. So that is using the Rice table. And then the Le Chatelier principle is determining the effects of stress on a reaction. Sometimes we call it a disturbance. Okay, so we've covered all of these topics. I'm going to spend today going through examples of different kinds of problems that you might see. I'm going to finish our problems with looking at acids as a very specific example of an equilibrium problem, because our next chapter is all about acids and bases. All right, anybody still need this? I did also on Chem 101 put some practice things. When I was looking over the exam reflections, several people said they wish they had more practice problems. So I put some practice problems both for Le Chatelier and equilibrium problems on Chem 101. So if you want to practice with those, you can. All right. A reminder, when we have heterogeneous equilibrium, which involves different phases, if there's a solid or a liquid, we leave them out of the equilibrium expression, or we just plug in the number 1 field. So here are some examples of equilibrium reactions that involve both gases and solids. This first one looks a lot like the one with the carbonate, only it's sulfide this time. So with this one, notice that we have 2 solids. So the only thing that's part of the equilibrium expression is the SO2. And so our equilibrium expression is just concentration of SO2, or if we're doing pressures, pressure of SO2, right? Okay, so in the second one, is there anything we're going to leave out? What, Maddie?
ES.
Yeah, the sulfur at the beginning. That's a solid, so we're going to leave it out. So it's going to be H2S over H2. Yes.
I have a question for 101. It said to look for KC, might not, what is KC?
KC means we're doing it in terms of concentration. KP means we're doing it in terms of pressure. Okay, so, and then the last one's a little bit weird. So take a second to try and determine what is that expression gonna look like. Oops. Right, what's going to be in the numerator on this one, the top part of the fraction? 1, because we don't have any concentration or any pressure for a solid. So we would just put 1. And so it's going to look like this. Okay. So remember to put a 1 and not a 0, because otherwise you would be saying the equilibrium constant is 0. All right, that makes sense? Okay, moving on. Looks like a couple of people still writing, so wait a second. All right, so this is a question I'm not going to answer here, but you can just plug in the numbers. So if you're given the numbers for the equilibrium expression, you just plug them in, but we're not going to do that. Okay, solving equilibrium problems. This is where we were on Monday. So we said we can do an ice table or a rice table. You put the reaction down. Underneath each chemical, you write the initial concentrations. And what do you do if there are no initial concentrations? So I have the initial concentration of A, I have the initial concentration of B, but it doesn't tell me anything about the C. So what do I write down for the initial concentration? 0. And that'll usually be products. So if it doesn't say anything about the products, we just assume the products are 0. Okay. For the change line, that's where we're doing the plus and minus X. Is our reactant, are our reactants going to be plus X or minus X? Minus, because they're decreasing. We have a lot of them, we're going to get less of them. So we do minus X. And then if I have a coefficient, I need to include that in there. So if my product is 2Z, I'm going to say plus 2X. Okay. And then for the equilibrium line, we just add up the concentrations from up above. So this is our concentrations or pressures at equilibrium. But the way the table is useful is I add the 2 rows from above it. Okay. So we're going to go to the problems on your paper and work out some of these different kinds of problems. Okay, so let's say I have a flask that initially contains 0.250 atmospheres of hydrogen iodide gas and nothing else. If the equilibrium pressure is 0.195 atmospheres, what is Kp? Okay, so we already have 0.250 plugged in for our initial concentration of HI. What am I going to plug in for the H2 and I2? 0, because they're products, so we can assume that there's nothing there unless they tell us otherwise. And what am I going to write for the change for the HI? We said it's going down because it's reactant, so it's going to be minus. Is it going to be just minus X? Minus 2X, because there's a 2 in front of the HI. Now my products, the only way they can go is up, right? I don't have anything to begin with. I can't have negative products, so they're each going to be plus X. And then for my equilibrium row, I'm going to add up the 2 things up above. So for the products, that's pretty easy. 0 plus X is just X. So under H2 and under I2, I'm just going to put X and X. The under HI, it's going to be a combination. It's going to look like an algebraic expression. All right, so now that we have this table filled out, we need to figure out what we're supposed to do with this information. So it says, if the equilibrium pressure of HI is 0.195, what is KP? Okay, so we can't set this stuff equal to the value of KP because we don't know what KP is. But we are given this 0.195. That is equal to the equilibrium pressure of HI, which is also this. So this expression is equal to 0.195. Does that make sense? So we're just going to say 0.250 minus 2x equals 0.195. Now, I apologize. The next slide, every time I click to advance it, it like makes everything else very pale, so it's hard to read. So I'm going to come back to this part, I promise, but this is the algebra we're going to plug in. Okay, so from here we can solve for x. Does anybody have an idea what they think x is? What do you think?
0.0275.
Exactly. 0.0275. Now, if you wanted to round this to 0.028, that's fine because we only had 2 sig figs to begin with. So that's okay. All right, so now we know what x is. So since we know what x is, we can plug in x to all of those places that x appeared in our equilibrium expression. So now I'm going to go back to the equilibrium expression. And everybody sees where this came from. Pressure of the products on top, pressure of the reactant, and then this is squared because there was a coefficient of 2. And from our chart, the pressure of H2 and the pressure of I2 in that bottom row are both X. So we're just going to plug in X for each one of those. And then the pressure of HI, well, we could plug in the 0.250 minus 2x, but we also have the number 0.195. So might as well just plug in the number. All right, so if we get to where we're plugging those things in, it looks like this. Don't forget to square this on the bottom. Why did we square that? If we look back up here for our equilibrium expression, this says pressure squared. And the reason that's squared is there was a coefficient of 2 in front of the HI. Good question. And so I come up with 0.0199 for that one. Which could be rounded to 0.020 because we only had 2 sig figs earlier. All right, questions on this one? Okay, so something to keep in mind is that when you have problems involving equilibrium, you're not always going to need to use the ICE table. So it's helpful to have a tool to remember when you're going to use the ICE table and when you're not going to use the ICE table. And this might be a good thing to write on your note card for your exam, so you can kind of refer back to it to help you figure this out. So there are two kinds of equilibrium problems. If you are given the initial concentrations and you need to find something at equilibrium, so sometimes it'll be find the value of the equilibrium constant. Sometimes it'll say find the pressure at equilibrium. But if you're given initial concentrations, or you're told this is what was put in the vessel, or at the start, lots of different synonyms for initial, then you're going to use that Rice table. But if you are given the equilibrium concentrations and not initial, so he said, okay, this is the concentration, we're already at equilibrium, you don't need the table because you're already at equilibrium. You already know what those numbers are. Plus, you won't have anything to plug in for oxygen. So pay attention to the wording of the problem so you know which thing you're going to do. Right, so the next question, it's a little bit tricky. I will try to be more explicit on quizzes and tests so that you don't have to kind of work around my wording quite so much. So the next problem on your page is about nitric oxide. And it has an equilibrium reaction with oxygen and nitrogen, which make up most of the atmosphere. And so we have an equation for it. Can I advance? Okay. So we are given Kc. Now, is this a very large Kc or a very small Kc? Very large. And I can tell that by looking at the exponent on the 10. So 10 to the 30th, that's even bigger than a mole, right? A mole was 10 to the 23rd. This is a huge number. So since this number is so huge, is this going to favor products or reactants? Remember that K is the products over the reactants. It's going to favor the products, which is good news for us because nitrogen and oxygen we're cool with. The problem with NO is if we count the valence electrons, we have 5 from nitrogen, 6 from oxygen, giving us 11. And 11 is an odd number. And what's wrong with odd numbers? What does that tell us about NO? It's a free radical. And free radicals are very reactive. They can damage cells. And if you're breathing this in, that's going to damage your lungs. Okay, so we don't want there to be a lot of nitrogen monoxide in the atmosphere. And because the equilibrium constant is so high, we're going to find out there's not going to be a lot. But let's go ahead and do the problem anyway. So we are given the mole fractions of oxygen and nitrogen. But remember, we can use the mole fraction to find the partial pressure. So my chalk, mole fraction is X. X times the total pressure gives us the partial pressure. What's the total pressure normally of our atmosphere? 1. So in this case, whatever the mole fraction is times atmospheric pressure is 1 is just going to be the same number. So we're going to pretend these mole fractions are the pressures. Okay, so let's go ahead and try and solve this problem. No, I didn't do this one line at a time. What's going to go in the numerator, the top? Just 1. And then we will put the reactants on the bottom. So it looks odd, but that is the way that it's supposed to look. So NH3 and HBr. All right. So always products over reactants. In each of these cases, all of the coefficients are 1. If I have coefficients other than 1, what do I do with those coefficients?
Here.
They become the exponents. All right. It's all on here. So first we want to have the expression for Kp. So much like the last one, pressure of the two products divided by the pressure squared of the reactant, and that's because there was a coefficient of 2. Now, there is a way to convert from Kc to Kp. I'm not going to test you over it. If you're interested in it, it's in your book. But when we do this conversion, we end up with 9.6 times 10 to the 20. So still a really huge number, right? And then we just plug everything in. So Kp is that number. Our pressures are the 0.781 and the 0.209. And then what we don't know is NO. So that goes on the bottom, but it's squared. Madison, you have a question? Figured it out? Okay. Yeah, Matt.
So where did you get the 9.6 times 10 to the 4?
So that's where I was saying I was giving you the Kc. In the past, I've had people convert between the two. What it amounts to is using the ideal gas law, in which case there's an RT in there. The R is the gas constant, T is the temperature. So just divided by RT. You will not have to do that. I will give you the value of K that you need. All right, so I ended up with 1.8 times 10 to the negative 59, and I promised this would be a really small number. Is it a really small number? Yeah. So maybe in this entire room, there might be one molecule of NO, but not something we really have to worry about.
We don't use the rice table to find this.
No, because, and I should have said that at the beginning. The air's been sitting around a long time. It's had plenty of time to come to equilibrium. So we were already at equilibrium. Now, if I took pure nitrogen and pure oxygen from pressurized tanks and pumped them into a container, then those would be my initial. And in this case, because K was so big, it probably wouldn't change a whole lot. Yes.
So why are we able to use the mole fraction as like the pressure?
Because mole fraction, so the question was, why can we use the mole fraction? Mole fraction times the atmospheric pressure gives us the partial pressure. So if I plug in my numbers here, I would have my 0.781 mole fraction for nitrogen times 1 atmosphere. And when I plug that in, I'm going to end up with 0.781 atmospheres.
So was that just like a we assume that?
Yeah. And it's always good to check your assumptions. But given the extreme size of the equilibrium constant here, even if we were slightly below or slightly above atmospheric pressure, probably wouldn't change anything. All right, do we still need this slide? Okay, so new question here. Sulfur dioxide plus nitrogen dioxide in equilibrium with nitrogen monoxide and sulfur trioxide. So I put these in different colors so that you can kind of keep track of things, because when we have such similar chemicals, sometimes it can be hard to keep track of these things. So it gives us the value of Kc, and it says at equilibrium, a container has these concentrations. So are we going to use a Rice table for this? No, because we're starting at equilibrium, so we don't need the Rice table. I promise we'll get back to a question where we do use the Rice table, but we don't need the Rice table for this one. All right, so I think a good thing to do anytime you are working on an equilibrium problem is to write out the expression for K. If nothing else, I'll probably give you 1 point just for being able to write the expression. But also, once you have that expression, you might start seeing where you can plug things in. So that's what I end up with. And I don't have any squares or cubes because I don't have any coefficients other than 1. And since we're not using a Rice table, we can just start plugging in numbers. So our Kc is the 85. Our NO is the 0.941. The SO3 is what we're looking for. So we're just going to call that X. The SO2 is 0.00124. And the nitrogen dioxide is 0.962. All right, so take a moment to try plugging in those numbers and see what you end up with. Does anybody have a number yet? Okay, that's very close to what I have. She said 1.077. Did anybody else get 1.077? So that looks a lot like the number that I got, but I got something a little different. Did anybody else get a different number? Is that a 0.1077? So you probably just either added or subtracted a 0 in one of the numbers there. Yeah. All right, so I rounded that to 0.108 more. I do remember that when you are plugging in numbers on the bottom of a fraction to put parentheses around the whole thing. Now, in this case, we're going to have to move those numbers to the other side. We're going to multiply both sides by those numbers. So we'll have 85 times the 0.962 times the 0.00124. But be careful with denominators of fractions. All right. Anybody still need this slide? So what about this one? We've got Kp for this reaction given to us, and it says a vessel initially contains 4 atmospheres of SO2 and 4 atmospheres of NO2. What is the equilibrium concentration of SO3? So do we need an ice table for this one? Yes, because we're given initially. Okay, now remember, initially might be at the start, or we put this into the vessel, but we didn't say the initially. So this is initially, so we are going to use an ice table. Or Rice table. So we start with the reaction. These arrows just go all over the place on this PowerPoint. And then we plug in our initial amounts. Remembering that since they didn't give us amounts for our 2 products, the products are just 0. Okay, so for the change line, this is the one that involves X's. So SO2 and NO2 are going to look the same. Am I going to do plus X or minus X? They're reactants, so are they going to increase or decrease? Decrease, so it's going to be minus. And then do I need any coefficients with the X? No, because the chemicals don't have coefficients. My products, the only way to go is up, so it's going to be plus X. All right, and then for the equilibrium line, we're going to add those 2 up. So 4 minus X, 4 minus X, and X and X. So now we need to solve for X. So we need the equilibrium expression, the products over the reactants. And we know that it's equal to 25.5. So we're going to set that 25.5 equal to products over the reactants. We were given pressure, so I'm doing this in terms of pressure. Sorry, I got shifted to the side there. All right, and so we're going to plug in 4 minus x where? Where are those two 4 minus x is going to go? The bottom. So it's going to be 4 minus x times 4 minus x. And then on the top, it's just going to be x times x. All right, now we could go through all of the, like we said, FOIL doing the first times each other, the last times each other, the outsides, the insides, and all of that. But what I notice is that I have a squared on top and a squared on the bottom. So really the easy way to do this is just to take the square root of both sides. So the square root of 25.5 is 5.05. And then the square root of the other side is going to be x over 4 minus x. So whatever I do, I'm going to make it so that you can avoid using the quadratic formula, because while I don't mind the quadratic formula, it takes a lot of time. So we're going to avoid it. All right, so the rest is just solving for x. So I've got 4 times 5.05 is my 20.20 or 20.2 minus the 5.05 times the x. That's equal to x. Get all my x's on the same side. And I find x is equal to 3.34. Always a good idea when we get back to when we get to the end of the problem is to say, did I answer that question? What was our question? What is the equilibrium pressure of SO3? So is X equal to the equilibrium pressure of SO3? Yes. So in this case, solving for X does answer the question, but it's always good to check. All right, I will post this PowerPoint so that you can kind of check some of these other things. I want to take a brief look at the very last problem on the back. This is an acid-base equilibrium. And so you'll notice instead of Kc, it says Ka. It's still Kc. We just label it as A because it's an acid. So when I take an acid, and remember, acids often have a hydrogen out front, and I dissolve it in water, that extra hydrogen attaches itself to a water molecule, and we end up with H3O+. This is the hydronium ion. Is that Ka very big or very small? It's small because the exponent on the 10 is -4. And that tends to be the case with our Kas, our equilibrium constants for acids. And so what ends up happening is that when you have on the reactant side our initial concentration minus X, the X is so small that we just pretend in that spot only it's 0. So for this one, we have our initial concentrations. Remember, we're leaving out the liquid water. We have the initial concentration of 2.5, and then we use zeros for the others. Our change is going to be minus X for the reactant, plus X is for the product. And then we add up those lines. So the top part is going to have x times x, just like we did on the last one. And the bottom is going to have the 2.5 minus x. Now for the top part with x by itself, the fact that it's really small matters, and it's important for us to leave the x's there. We can't just put it as 0. Otherwise, we're just going to have 0 as our final number. We don't want that. But when we're doing the subtracting off, we're going to say x is a lot smaller than that 2.5. So whatever number it is, when I subtract it off, I'm still going to basically have 2.5. That's why we can ignore that. So this is what that looks like. We plug in the Ka, 3.5 times 10 to the minus 4. The x squared is on top because we have both the hydronium and the fluoride, x times x. And on the bottom, we have our 2.5 minus x. And then we assume x is very small when we're adding or subtracting it. And so we're just going to leave it out. And then I should probably put another line in here. Then we're going to take that 2.5 and multiply it by the Ka. So if you take 2.5 times 3.5 times 10 to the minus 4, that's where that 8.75 comes from. Then when we solve for x, we get x is equal to 0.0296. So if I subtracted 0.03 from 0.25, would it make much of a difference in the size of that? Not really. And in fact, if I'm obeying my sig fig rules, it would still end up as 2.5. Okay. So for all acids and base equilibrium that we do, we will be able to make this assumption that that x is really small. Now, there are occasions when we have a fairly strong acid that we can't make that assumption. But we're trying to simplify things, so we will make that assumption each time. Okay, questions about these? And I will make sure this PowerPoint is posted this afternoon so that you can look at the other problems. What I want to do now is take a look at the Le Chatelier principle. I always call it Le Chatelier's principle, but I think it's actually the Le Chatelier principle. There's no apostrophe S there because I always get spell checked. Okay, so we've talked about adding and removing reactants, right? And products, and we talked about adding and removing heat. And so we said when we add stress, we can do by adding and removing heat or chemicals. And what we do is move away from what we added. And move toward what we removed. Okay. So I'm going to give you a couple of different scenarios. What if we add a catalyst or an inert chemical? What does inert mean? It means it's a couch potato. It does nothing. Okay, so the noble gases are inert. They do nothing. So if I have the reaction A plus B in equilibrium with C, and I add Q, Q is some chemical that is not part of that equilibrium. This rule says I'm going to move away from what I added. Well, that doesn't appear in here. I'm going to move towards what I removed. It still doesn't appear in here. So how does that affect this? It doesn't. catalysts and inert chemicals do not affect equilibrium. Okay? Okay. What if I increase the volume? Here I have to think about how does that affect concentration or pressure? They're both affected the same way. So if I increase the volume, say I dilute something, I add a whole bunch of water, what's that going to do to the concentration? What did you say? Decrease? Yeah, it's going to decrease all of the concentrations, because if I add water, and I'm not adding A, B, and C, all of the concentrations go down. Okay, if I have gases and I expand the volume of my container without adding any more particles, what happens to the pressure? Pressure also goes down. Okay, when this happens to everything at once, what we have to pay attention to is the number of particles on each side, okay? So if I increase the volume by doing one of these things, then I'm going to move in the direction of more particles. So A plus B in equilibrium with C. If I dilute all of this, if this is in solution and I add a whole bunch of water, this is going to move in the direction of A and B. If these are gases and I expand the container, there's more room for all of those particles to take place. So when C breaks apart to form A and B, it's harder for A and B to get back together because they're farther apart. They collide with each other less often. And so we shift in the direction of A and B. Okay. And then the last thing is that the equilibrium constant is constant at a given temperature. So all of these changes do not affect K. If I increase the volume, K is the same. If I add a chemical, K is the same except one. Which change is going to affect K? Temperature, because K is at a given temperature. So if I change the temperature, I'm going to change what K is. All right, so that kind of covers everything. Questions? All right. I'm going to let you hold on to those packets so that you can use those in reference to your quiz. I will collect them on Friday. So yeah, take a look at those. Take a look at your notes and begin studying for your exam. I will see you on Friday.